Welcome everyone. My name is Natan Silnitsky, and I'm a backend infrastructure team lead at Wix.com. And Wix has a lot of scale, huge scale, and we have created our own event-driven architecture for 2,200 microservices in production. And this talk is about the key event-driven patterns that I've implemented or have witnessed implementations of at Wix that have enabled us to create a robust distributed system which can easily handle increasing traffic and also storage needs. So a few words about Wix. We have more than 200 million registered users from 190 countries. More than 100 million websites have been built on Wix, more than 5% of all internet websites, more than 200 microservices, and 2.5 billion Kafka messages produced every single day. So we have a lot of different event-driven use cases that we can learn from and find the best patterns. So in this short talk, we will talk about 4 different event-driven patterns. The first one is consume and project, how you can split up a monolithic design and use events in order to be more flexible in deployment with microservices. Event-driven from end to end is the second pattern, how we can deploy Kafka together with WebSockets to get to a pure event-driven architecture all the way from the browser to the end of your backend flow. Zero latency key value stores is an interesting case of using, having storage that you can easily query because it's in memory, that is populated from the Kafka topic and is also continuously updated from it. So really interesting use case. And also events in transactions. So how can we guarantee that processing happens exactly once, which is very critical for some parts of our business, like with payment flows and stuff like that. How we guarantee that when we process our events, it only process them exactly once. Okay, so we used to have the monolith as our building block. And we decided that we want to deploy these services separately and also scale them separately, the different areas of our monolith. So we split them up to a distributed microservices environment. Now, if we have one big shared database among these services, then we probably have mutable state that is shared, which is bad because there could be a lot of simultaneous work that can perhaps cause data corruption. And there could be a lot of contention for the same database instances. And also it means that if you use the same database for all our microservices, it means that we won't have a flexibility of choice of using the best database that our microservices requires. So with microservices, we've encapsulated the data behind our microservices. That's great. We have flexibility. You want a time series database? Go for it. You want a graph database? Why not? And also the schema evolves separately because, and it doesn't hurt to change the schema because it's hidden behind your API, the microservice. So if you have a relational table, you can change that to your liking, and you don't need to talk to any other team about it. Now, it's looking nicely, but what about communications happening between these microservices? So we have a classic e-commerce flow with a checkout service, and it requires to communicate with payment service, user service, inventory service in order to complete a checkout. So with a request reply model, you will have these HTTP or RPC calls coming from the checkout service as a client to the payment service or user service as a server. Now, this request reply model can be quite slow because now our databases are hidden behind the microservices API, And if you need data from all of these different services, then you need to gather them one by one and then aggregate all the information. So that can be quite slow. Not only that, we can have sometimes network issues to a specific service, or maybe it's currently unavailable for some reason, it has a problem. So that's a big issue. So what will we do with our incoming requests that we need to process? And we could have a cascading effect here where one service calls another service, calls another service, calls another service, and the most downstream service has an issue. So now the error will propagate all the way back, and we have a lot of timeouts in our system. And what if there's a momentary error and you want to overcome it? So you'll need to create your own retry mechanism in your service to make sure that you end up successfully getting the data that you require. So a lot of issues in terms of networking here with the request reply model. Now let's see if we can gain something by actually introducing a message broker in between the services. So here we have a message producer and a message consumer, are like before we have a client and a server. And by only just introducing this broker, we can already really increase the reliability, because Kafka has, a message broker usually will have replication and will have a cluster of many brokers that replicate the information between them. So once the message is produced, we can be safely sure that it will then eventually be consumed. Now, interestingly, when you work with the event-driven model, the flow control is no longer controlled by the sender here. It's actually controlled by the consumer. So actually, when you do request reply, then the server is the one that is in charge. It needs to gather up the response and get it back to you. And if it's unavailable, well, what can you do? Now here, actually, the server that we talked about in a client server is acting here as a producer. So it's producing events and then forgets about them. It doesn't care who consumes these messages or events. Its role is finished. Now it's the responsibility of the message consumer or the client in the client server architecture to actually consume the message and be in charge of what to do with it. So there's no interaction directly. There's decoupling, which is always a good practice for your architecture. And the consumer will be in charge of actually deciding when to consume the messages, when to process them, and what to do about them. So specifically with Kafka as a message broker, we have a very sophisticated design, which is based on a simple mechanism of distributed log files. So each topic is just made up of partitions, which are commit logs, log files. And a message is produced to one of these partitions. And while processing will be done sequentially on each partition, you can increase your parallelism and work quite easily by just adding more partitions. So your scale can grow linearly. Now the producer will just append the new event or message at the end of each partition. So it already gives you a sense how easy it is and fast to produce messages, because you just append them at the end of the file. And these messages can be kept indefinitely, unlike traditional message queues, where messages will get removed when the consumer actually consumes them and processes them. And this immutable structure is great because you can have as many consumers you want, and you can start them up whenever you want and consume these messages separately. So each consumer in Kafka has their own pointer, their own index of what is the current messages that they are processing for each partition. And once they are done with the message, they then commit it. But it's not removed from some queue. It is just kept in a journal that this is the last committed message for this specific consumer group. And then when it restarts, because there's a new version for this service that has the consumer or something like that, it knows exactly where to start from. And this is a very powerful concept. This immutability, it means better performance, better resiliency, and much less data corruption, unlike traditional message queues. So like I said, you restart and then, or there's some network issue. Once you gain your footing back and everything is okay in terms of technical stuff, you just go back to process from where you left off. It's that simple. So you eventually consume the messages and process them. Okay, so let's go back to our e-commerce example. And here we have our checkout service that requires to have a lot of data found in other services in order to complete the checkout. Now let's look at how it will look with event-driven model. So with event-driven model, we'll actually have specific topics that each of the services is in charge of. So the inventory topic is in charge by inventory service, and it will produce updates about what's going on currently with the inventory. And it may listen to other topics in order to update the inventory. But you as a consumer can know what's going on with the inventory by just listening to this topic. And you can create your own caches in your service in order to know what's going on with specific elements that you are interested in. Now, so checkout service listens to inventory topic, cart topic, users topic, and then it can get all this information without these services even knowing that there is a checkout service. It's not interesting to them. And then the checkout service will actually be in charge of producing new events to orders, because we want to have a new order in place now that we want to complete checkout. So the payment service will listen to these order requests, and then it will process the request. So you can see we have a much more decoupled system here with services not knowing about each other and actually saving the data that is interesting to them close to their heart, to their geography. Now, this is a very high-level overview, and I hope that the patterns that we're going to discuss now will help you understand more and get you more into this concept of the event-driven architecture. So all these patterns are used daily by Wix, microservices, and I wrote a blog with a few more patterns that I will share with you the link at the end of the talk. So these are battle-tested patterns that you can be safe to use. So we're talking about consume and project, how we can create materialized views for our database from using Kafka topics in order to make sure that we have the data optimized for possible querying by different consumers and users of our data. And we can also split up the monolith by doing that, and we'll see what it means. Event-driven from end to end, we're talking about the pattern, how we can have streaming of events all the way from the browser to all of our microservices ecosystem by using Kafka and WebSockets together. Zero latency key value store. We're going to talk about having storage that is continuously getting updated and easily and very fast way of fetching this information in memory, all using Kafka, and how we can process these Kafka events exactly once for critically important business flows. Okay, so we're talking about consume and project pattern. Here we are seeing one of our more important basic services that handle a lot of basic infrastructure for our different microservices. It's called the meta site service, and it is in charge of a lot of flows. For instance, which sites are installed, which applications are installed for each site. What is the site version? Who is the site owner? So a lot of metadata that's related to Wix websites. And this data is very important for a lot of our services, a lot of verticals, like Wix stores, Wix bookings, and Wix restaurants. Now, meta-site service used to be a lot more monolithic, and it had like one big database with all of the large meta-site objects with all the information put in it. So it got to more than 1 million requests per minute on this database for reads and write, and it became too overloaded. So what did the meta-site team decide to do? They decided to take one of the most popular queries about which apps are installed in the site, this installed apps context for the site, and split up all this traffic from the meta-site service. So start splitting off microservices. The first one is for this specific context. So how did they achieve splitting it in a safe way and a performant way? They started off with producing any updates happening on the meta-site database to Kafka. So we just have site updates events, and of course, all the historical information also is Kafka events. Then they created a completely brand new service called a reverse lookup writer. And this one just consumed these Kafka event updates for these meta sites. And it's only interested in updates regarding site installed applications. So it just filtered for the messages that it is interested in and only took the parts of the message that it's interested in and wrote them to a completely brand new database table, the installed apps context. So they consumed the event and projected it to the dimension that they care about, not the entire site, just the apps installed on it. Now we want our users, our Wix restaurant service, etc., to actually be able to query and get this information. So for that, they created yet another microservice called a reverse lookup reader. And this service accepts RPC calls and just reads from this database and answers questions, queries. Okay, so we created two new microservices. Why not just the one? So we decided to, the Metasite team decided to split the read and write service in order to gain flexibility. So you can just take your database, your new database table, and replicate it for read-only queries. So we have new read-only database instances, and those can be scaled up and deployed all around the world, as many as are required from the read traffic load. But you really don't need so much load for the write flow. So you just have the original master database write flow, and that is handled by the writer service. But the reader service can be deployed around the world and just read from the read-only replicas of the data. So it's much more flexible deployment scenario, and it can reduce costs. So you don't need to have the write side scale up as much as the read side. And what this database table has created is a materialized view. So it is actually optimized for exactly what the query is looking for. So the queries are much faster now. And because we just produce, the Metasite service just produces these events and doesn't care anymore about serving requests, then there's a massive load reduction on the original Metasite. Okay, so Metasite team was much more happy and needed to do a lot less production incident handling after this split. And you can also use it maybe in your use case, or if maybe you have a monolithic use case. So let's look at the second pattern, which is event-driven from end to end. So imagine you have a long-running asynchronous business process. And for instance, we're talking here about Wix wanting to offer its users the ability to import contacts into the Wix platform to manage all the site visitors, like importing contacts from Gmail or stuff like that, maybe sending them announcements, what's going on in the site, etc. Now, this process can sometimes take a long time depending on the third-party API. And we want to keep the user updated on these contacts importing flow. So we can do this all with request reply style and keep like status in a database and have the browser keep requesting to get updates. But how can we do this completely in event-driven style without any polling? So let's see. So we have two services involved. We have the context job service that actually creates jobs of import, like splits them to chunks, these jobs. And then we have the dedicated import service. So we have an import service for Gmail, import service for Microsoft, and dedicated and knows what it needs to do. So how do we do this event-driven? So we can have the browser subscribe to get notifications from the HTTP to WebSockets. So we have a channel of the WebSocket. The channel ID of the WebSocket will be part of the request to start the import process. So the jobs service gets a request to import CSVs and or from Gmail, etc. And it also includes the channel ID. So it will split up this request to specific chunks of data, and it will produce these commands to Kafka, including the channel ID. Then the actual importer services can consume these events and start actually the importing process. And they also get the channel ID where they need to return notifications to. So once they are completed, they can send an event to the WebSocket service. Hey, please tell the browser, notify the browser that I have finished importing. And here, this is the channel ID that you can send a notification on. And then the WebSocket service will return the notification to the exactly correct browser. Now, what's interesting about using Kafka in this case is that it can really help you if you have cases that require cross-DC communication. For instance, maybe there is some source of contacts that is only found in Asia, and you want that the importing done from that source to be done only in your Asia data center. So that's not a problem. You can make sure that you produce requests to import to Kafka and have it replicated to the correct data center. And then these consumers will know that it needs to handle it because it's relevant to this Asian source of contacts, and it will handle it. So everything is done completely seamlessly here. So what have we learned? We learned that we don't need to do any polling or create complex status database tables for getting polled, and maybe we'll need to do optimistic locking on that and all these annoying concurrency issues that we have at databases. We simply notify the user on any status change via WebSockets. And it's really scalable, a really scalable solution. You can spin up as many importer services that you require, and then create as many jobs as you require, and they will just, each one will take the correct job and work on it. Completely decoupled, completely unaware of each other. And then we can easily set up replication between our data centers, between different Kafka clusters, and easily set up geographic specific location for contacts importing if needed. So it's really easy to add cross-DC communication. Great, so we have our modern event-driven style all the way from the browser to all of our microservices. That's great. And the third pattern is the zero latency key value store. So we're talking about a special kind of storage. So you can think about Kafka topics not only as topics of events that you want to consume, and then maybe after a week, old time events are deleted. You can also have Kafka topics, have the partitions be like storage. So they can be compacted and only keep the latest value for each key. So there are key value stores. You can think about using Kafka topics as key value stores, and you just set them for compact mode. And then if you have these Kafka topics used as storage, you can actually load them into memory really, really simply. And then you'll have zero latency key value store in memory. So we at Wix have implemented our own key value store reader implementation that simply has an in-memory map and a Kafka consumer. And this consumer reads this compact topic, and it loads everything into memory on startup. And it sees that key one has a new value with v2, so it updates the in-memory map. And when everything is finished, you will have an up-to-date in-memory map that you can start using in your service in memory. So it's really fast access. Now let's look at a few business examples using these key value store readers. So for instance, our business manager service that helps Wix users with managing their business has a key value store for all the countries that Wix operates in. So you can like choose your country in the drop down or something like that. So now all it has to do is create a compact topic and start loading the information into memory. And booking service is in charge of Wix users that offer schedules like yoga instructors and stuff like that. It's like bookable lessons and stuff like that. And it's very important when scheduling stuff that you know the correct time zone. So it has here a dynamic configurable key value store of the available time zones for each country. And other than readers, we also have abstracted key value store writers. So the business manager can update anytime that a new country where Wix operates in, it can update this key value store. What happens behind the scenes is basically, it's just a Kafka producer. So we have a new country like South Sudan. So we just produce this key value to the country's compacted topic. And then, interestingly, we can have seamless updates to other services that are interested in consuming these countries and have them as part of their in-memory key value store. So Bookings is also interested in the country's key value store. So it has an in-memory KV store reader and has a consumer for the same compact topic. And it gets an automatic update whenever it's updated, including here with South Sudan. So now that Bookings has accepted this new event that has a new country, South Sudan, it can actually now automatically add the time zone needed for South Sudan. So it also has a key value store writer for time zones. It finds the correct time zone for South Sudan, puts it produces this event to Kafka, and now its key value store reader for time zone is automatically up to date with the time zone for South Sudan, which is great. And of course, other services that are interested in time zones can also set up their own key value store readers with their consumers and get their up-to-date time zones automatically as well. So you see this like interesting event-driven pattern that the producers of these events don't care who is going to consume them, but these consumers can get automatic new events because they're listening to updates. And so your data can be spread around all of your services and be used seamlessly without needing each service to know about the other service, completely decoupled. So what have we gained? We gained loading compacted topics to memory, which means we have zero latency key value stores, where we can put dynamic configuration and it can be accessible for any service that is interested in it. Compacted topic is still a topic, so other services can consume it. Now, an important note here is that this pattern is only useful when you have small data sets that can fit into memory, because memory still costs money. It's not infinite. So you want to make sure that for large database sets, you don't only use an in-memory solution, but you actually stream the information to a more persistent store. At Wix, we actually use AWS's DynamoDB because it offers infinite scale. And we can put, when you have very large data sets, we put the information in DynamoDB, and then we can stream the events from DynamoDB using DynamoDB events. But that's out of the scope for this talk. I had other talks that talk about how we use DynamoDB together with Kafka. And our last pattern for this talk, which is events in transactions. How to make sure that you process events exactly once in an idempotent fashion. So idempotency means that no matter how many times you try and do something with the same information, you won't change the state of your data. So it's kind of a deduplication. It's idempotent. It doesn't change no matter how many times you run it. So how can we make sure that we are able to work even though we may have messages that potentially get produced more than once? So usually that is handled by the application level. But let's see how Kafka itself has handled that for us in order for us not to need to do this idempotency deduplication work in most of our flow. So we can go back to our classic e-commerce flow, and we have a payment service, and it wants to announce that payment has completed, so it produces it to Kafka. Now we have our famous checkout service. It consumes the fact that payment has completed, and now it wants to announce to the world that the order of the checkout has completed, and it is enumerating all the items that are part of this order. Now we have a lot of other e-com services that are interested in this event. We have delivery service that now that order has completed, it needs to deliver the items that are found in the order. Inventory is definitely very interested in consuming this event because it needs to reduce inventory per each item that has been paid for. And invoices service is also interested because it needs to send out invoices for each of these orders that are completed. Now, we really don't want to have delivery service starting to deliver items twice, right? Or inventory being reduced twice, or sending 2 invoices or 3 invoices because we unfortunately got the messages more than once. So how do we solve this? One way to solve this is to, like I said, do the deduplication by ourselves. So we have these services that need to set up, each one needs to set up their own completed orders table. And if it gets like the order ID in the event, it keeps it in the database. And then it needs to make sure that it will write down that this order has already arrived, and no matter how many times it was produced by payments or by the checkout service, you will need to first access the data and see whether it was already successfully completed or not. And each of these services will need to handle deduplication by themselves. Now let's see how Kafka can help here. The Kafka producer, you can enable idempotence by just rating a flag, and then it will make sure to produce messages exactly once. How will it do that? It attaches the offset of each message to the message. So let's see how idempotent producer works. It produces a message, including the offset. So then Kafka broker sees, okay, I got a message. This is offset 0. Great. Now the idempotent producer will increment the offset for the next message, and it will produce it and say, okay, great. We have one. We are getting the message, and it's offset 1. Now, if for some reason the producer will send the message twice, it will still be with the same offset. So the broker said, aha, I see that offset 1, I already have it. So I'm just ignoring this message. I already have it. I don't want to get any duplicates. Now, for the rest of the streaming here of the events processing, including the consumer and the producer in the middle, and then the downstream consumers, you can actually set up a Kafka transaction. I wanted to get into too much detail because it's too broad a theme, but you just set up a Kafka transaction, and then you can consume it, and the consumers, the downstream consumers, will only consume messages that have the transaction has been completed. So even if there was some error and messages were perhaps getting twice, the transaction will be aborted and the transaction will start again. So all the messages before that will be disregarded, and only when transaction is completed, then the consuming will start, meaning that we get messages to our downstream topic exactly once. So what is useful in these transactions? So first of all, these transactions are quite complex. There's more boilerplate for producing and consuming in this regard, and you will need to do performance tuning. You have a trade-off between the overhead of this transaction and with the transaction size. So the smaller the transaction, the bigger the overhead will be for maintaining this transaction. But the lesser the latency will be for the downstream consumers actually reading this transaction. Now, the bigger the amount of messages in the transaction, then smaller overhead of maintaining these transactions, but the higher latency. And of course, the downstream consumers, the final consumer, has some side effect outside of Kafka. So Kafka can't really handle that exactly once because it's the responsibility of the processor at the end. But you can actually do deduplication by using the Kafka record offset as your version. So it really simplifies deduplication at the end. Now, I wouldn't recommend turning on transactions by default, but only use them in very specific cases like payment processing.
Before moving forward, just wanted to let you know time is running out, so we can maybe do the rest in speaker chat.
Yeah, this is one of the final slides. So if you want to understand more about exactly one semantics in Kafka, I have a dedicated talk for that, and I put all the links for you. Don't worry about it. So just to summarize, Wix developers have employed all these event-driven patterns to make their microservices more decoupled, more resilient, and more scalable in order to have a mature distributed system that is deployed globally and is safe to operate. And you can also check out our great high-level SDK for Kafka if you're using the JVM, which calls Greyhound. It's had a lot of cool features for performance improvements, for resilience improvements. It's really great. I really hope that you check it out. And I would like to thank you very, very much. And here I have extra resources for you on the slides. So about event-driven architecture, my blog posts, a great set of blog posts on how to think about your microservices when you do them in event-driven style, and the talk I gave on exactly once semantics, And I put all of the slides with all of the links I slide share. So you only need to look me up on SlideShare, Natan Silnitsky. That's my name there. And you can follow me on Medium and Twitter to get all kinds of updates on everything we do in infrastructure and Wix around event-driven architecture, around Kafka, around caching, everything to do with software engineering. I give updates on Twitter and also on LinkedIn. And of course, you can visit my website, natansil.com, to get information on all previous conference talks I gave, blog posts, and that's it. So thank you so much. And Pardis, do we have time for Q&A during the session, or we will need to move over to special chat?